go ahead and get this thing rolling. So let's just talk real quickly about what we should have seen here in the lab. And I'll try and kind of spread the wealth here. Let's go over here to Annie. Did you see the bulbs light at exactly the same time?
Yes.
Okay, and I think that's a pretty good answer there. Do you believe, Annie, that the bulbs actually lit at the same time? And this is a more interesting question. What do you think?
This one I was a little bit yes and no because
Uh-huh.
I saw them light at the same time, but I wasn't sure if it actually the the power traveled at the same time, like
Okay.
reached them at the same time.
Yeah.
So I
And
didn't put an answer for that one.
and that's okay. All right. So this one is sort of your opinion. And so you can kind of go however you wanted to on that. We're going to talk about what is actually happening here and get to an answer to that question here through the course of today's little mini lesson. And then Annie, since I still got you there, did the bulbs appear to go out at exactly the same time?
Yes.
Yeah, and I think the key word there is appear. So I'm kind of trying to give you like, hey, plant some seeds of doubt. All right. I think that they appeared to for sure. All right, Annie, thanks a lot. Let me go over here to Adam, if you can get yourself ready here. So when you broke the loop, is there any place you can break the loop and the bulbs would stay lit? Oh, we lost Adam for a second.
I'm gonna be honest, I didn't get to this lab. I'm
That's
sorry.
okay. That's all right. Let me that happens. Anna, did you get this?
I got the lab, but I didn't see anywhere on the circuit where you could break it and still keep both bulbs lit.
Okay, so is there any place you would say no?
Yeah, that looks right.
Okay, all right, I would agree with that. And that's a key point about electrical circuits. If there's a break in the circuit, it ain't gonna work, all right? Anna, since I got you there, let's go ahead and do number 4. With the loop complete, make one break anywhere. Do the bulbs light without actual contact? What would you say?
No.
No, all right, so we gotta have actual contact. And do you think actual contact is needed?
Yes.
All right. So we'll talk about some of the meaning of those, but I wanted to go through answers to that real fast with everybody. All right. Now we go to the second page, and basically what I've done is I've taken what we would have done in class and I've reworked it so that we can do it with this simulation. And my hope is that the simulation wasn't too difficult. So thank you, Anna. Good morning, Ethan Bennett. Ethan, how are you doing? You hearing me okay?
Yeah.
Okay. So listen, I don't know if you did you manage to do this lab or no?
Yeah, I did.
Okay. So as we look at these, do you mind giving me answers here? Was this circuit A gonna light or not light?
No.
No, does not light. What about circuit B?
No.
No. And there's some problems with each of them that we're gonna talk about here in just a second. And then Ethan, what about circuit C there, bud?
No.
Nope, nope, a whole bunch of failure right there, okay? So based on the experiments, what factors must be met in order for the light bulb to light? Do you want to kind of take a stab at that, Ethan? Am I putting you on the spot too much?
I think they just have to be like a closed circuit, and it has to be on either end of the battery.
Okay, so we got to have either, is it either or both ends? What's the better word?
Both ends.
Yeah, I got to have both ends of the battery, and we're going to summarize this here in just a couple quick moments. We got to have both ends of the battery. And now if I go back and I look at this, not a single one of those has both ends, all right? So that doesn't meet that criteria. And the other thing that's really kind of important is we've got to have what we call a continuous conducting path. And we're going to talk about conductors versus insulators here in just a couple moments. So we got to have both ends of the battery. We got to have a continuous conducting path. And we have to have the right parts of the bulb involved in the circuit. All right, right parts of bulb, how to say involved. All right, so Ethan, thanks so much, bud. Good to see you this morning. And let's go ahead and look at the last page. And this is where I would expect that maybe you had a couple of questions. The little Wikipedia link is pretty, it's good information, but it didn't necessarily answer these questions here. So I'm gonna go ahead and just tell you what these things are because this is not hard, this is just glass. All right. Someone chime in. Anyone know what this little guy, the little squiggly guy, is called?
Tungsten filament?
Oh, was that Emily Larson?
No, that's Anna.
Anna, fantastic. All right. Having to identify you guys by voice is a little bit tricky. So I got the tungsten filament. Inside here, all right, inside is usually an inert, which is usually a noble gas. Typically it's argon, inert noble gas at low pressure. And then these two guys, typically they have names that are the thread, and this is pointing to the very, very end. This is called the tip. And these are the basic important parts of a light bulb. This technology isn't really new. Edison figured this out, perfected the design. There were plenty of other people, but Edison's design over 100 years ago, we've just now started to tweak this, but this was what worked for a super long time. We basically pass electricity through this tungsten filament, which is an extraordinarily thin wire. And when you pass the electricity through a very thin wire, there's a lot of friction, so you get a lot of heat. And some of you may have had like an easy bake oven when you were a kid. You're literally cooking over the heat of a light bulb in an easy bake oven. So let's see here. I want to get a little bit further along here. Let's run through this real fast here. I think, who have I not called on yet? Hey, Jennifer Overdahl, do you have the information for this lab, or do you at least remember it?
I didn't get to it yet.
Okay.
Sorry.
No big deal. Maud, what about you?
I haven't done it yet.
Okay. Let's see here. Ben?
I did it.
Okay. Ben, run us through some answers here. When you insert the dollar bill into that little break in the circuit, did the electricity flow?
No.
Nope. Paperclip?
Yes.
Yeah. Coin?
Yes.
Eraser?
No.
Hand?
No.
Dog?
No.
Yeah, don't put your dog in a circuit. Pencil?
Yes.
All right. So there's properties to these things, and I want to just run through that here in our little miniature lesson. So any questions on the lab real quick before I set that aside? Okay. So if I'm in your shoes and I want to kind of make sure that I'm understanding some interesting things about circuits and introduction, here's what I'd say, all right? What is a circuit? I'm going to go ahead and say that a circuit is a continuous conducting path between the positive and the negative ends of a power source, power supply, and in the case of the lab, I think you would sort of understand that the thing that was providing the power source, power supply, was the battery. All right, now, key word here, conducting path. So I want to talk briefly about the difference between conductors versus insulators. All right. If I had to put someone on the spot here, I'm going to grab Emily Larson here. Emily, from an electrical standpoint, what is a conductor?
Something that can transfer electrons.
Yeah. Conductors allow easy movement of charge. And typically, coming back to you there, Emily, allow easy movement of charge. What's the material that typically we associate with the ability to be a conductor?
Metal.
Yeah. Conductors are metals. Aluminum, gold, copper, zinc. When you think back to chemistry, there's a whole bunch of metals on the periodic table. Metals are conductors because they have free electrons. All right. Thanks, Emily. And if that's what a conductor is, an insulator is basically the opposite of that. An insulator does not allow easy movement of charge. Oh, I'm running out of space. Movement of charge. And there's all different kinds of insulators out there, all right? Some examples of this would be wood, plastic, styrofoam, and I could make it a really long list, but it's easiest just to say not metals. All right, so we have to have a continuous conducting path, and it has to be made of metal, and it has to connect up between the positive end and negative end of a power supply or a battery. All right. Now, the only other thing that I wanted to touch on here real quick is when we look at sort of your traditional light bulb. So traditional light bulb. In order for those light bulbs to work, all right, I'm going to draw this up. Here is the thread, here is the tip. And if I put a battery over here, and this is one of the drawbacks to the little simulation you guys are playing with if you did the lab, all right? Understand that this little nib part, this part that pokes out, is always the positive end of the battery. And this is the negative end of the battery. So here's a question for you all. And I'm gonna throw this out to, let me get Maud looped in here. Maud, I wanna draw 2 lines, and the lines are gonna represent wires, all right? If I wanted this light bulb to light up, and remember that there's a wire coming from the thread, here's the filament, and there's another wire that goes down towards the tip. I want you to tell me, Maud, where should I put the wires so that I could make this drawing a quote unquote complete circuit?
You'd have to put one from like the filament to one side of the battery and then the other wire from the other side of the battery to the tip.
Okay, so I'm gonna work backwards. From the tip to one side of the battery. Does it matter which side of the battery I go to?
No.
Okay, so I'm gonna go ahead and just draw it over to the positive end. And then you said from the filament to the other side of the battery. So kind of be real specific. If I draw a line, can I actually touch the filament with my wire?
No.
No, so be specific. Where do I need to draw from?
I'm not sure what it's called.
How about if I point to this area? Is this the
Yeah.
area you're thinking of?
Yeah.
Yeah, this is really hard to do over video chat. This is called the thread, Maud.
Okay.
So this wire is touching the thread. So now that you know the word, I'm gonna go from here to the thread, all right? Because literally this wire is touching the thread goes around the entire light bulb, all right? And if you ever change a light bulb, you know that that's what's going on. So those are sort of the key points that I wanted to get at here. And so with that, I think you guys have all the pieces of information that you need to tackle the work that I've assigned for today. So I'm gonna speak now or forever hold your peace. Do I need to leave those notes up for anybody? It is recorded, so. All right, I'm gonna go ahead and get rid of this. And now, today's assignment, all right, is I've got, and you're just gonna print these out and you'll answer these questions here. I'm thinking as I look through these, let's see here. You know what, one thing I've not talked about? Let's look at question number 5 here. It says, what happens in the wires when the battery connections are reversed? What is your evidence? Someone that has done the lab, Ethan, I think you said you've done the lab. Ethan, how many directions did the electricity flow in at any given time?
Seemed to be just one direction.
Yeah, and so if I had to go back and maybe I want to squeeze this into a little bit more on my notes page here, all right? So we're gonna be talking about, there's actually 2 different types of current. There's direct current, and then there's alternating current. So let me get this in your little brains here, and then we'll be kind of wrapped up. Direct current, also known as DC, right, is electricity that travels in only one direction. kind of like that amazing band from a couple of years ago. And that's the kind that we will be investigating, right? This is us. We're going to be studying only direct current. And the reason for that is the other one, AC, which is alternating current. AC is electricity that is sort of schizophrenic. It goes one direction and then the other direction, one direction, the other direction, and it literally just wiggles back and forth, back and forth, back and forth. Whereas direct current literally just goes in one direction. So when we look at a battery, and I hook up a battery, and I'm going to put, and this is a little symbol that we'll use later on. That's the symbol for a resistor, all right? If I have the positive end of the battery here and the negative end of the battery here, electricity is always going to flow. If it's a direct current, we're going to be talking about electricity that goes from positive to negative, all right? The electricity doesn't go in any other direction. So, and I'm coming right back to you, Ethan, here. So if I take this battery and I switch it around, what did we see about the direction of the electricity flow?
It's now going the other way.
That's it. Because electricity is always, for us, in this sort of entry-level regular physics class, electricity is going to go in one direction, from positive to negative. And just to kind of give it away a little bit, we didn't know what was moving once upon a time, but once we started to understand that there's protons, neutrons, and electrons, what's actually moving is we have electrons moving in the circuit. All right, last little thing here. I think it was Annie at the beginning where we were talking about whether the things lit up at the same time or not. And here's what I want you guys to visualize. If I think about this circuit right here, there are literally electrons everywhere in the circuit. If I take the battery out of the circuit and all I have is a wire, a resistor, and another wire, there's no reason for the electrons to move, okay? And because we can't really see electricity, I'm gonna give you an analogy. Let's think about marbles. And those marbles are all sitting on a little tray or a track or some sort of surface, and it's perfectly level. All right, I'm coming back to you here, Annie Brickley. If these marbles, which are all sitting all snug up against each other, if it's on a perfectly level surface, is there any reason for the marbles to move, Annie?
No.
No, none at all. And that's kind of like what we have in this picture right here. There's electrons everywhere in the wire, in the resistor, in the wire. There's electrons everywhere, okay? Just like there's marbles everywhere. Annie, if I take and I tilt this surface, would the marbles then begin to move?
Yes.
Yeah, absolutely. There's no doubt about that, okay? And the really cool thing is it's not like this marble moves and then this one moves. They literally all move at the same time because they all have now a reason to move. They all move simultaneous, all right? So I'll say non-level here. And the reason that they move is because there's a difference in energy between this point and this point. Here we're talking about gravitational potential energy. The thing that makes the charges move here, Annie Brickley, what am I drawing?
A battery.
Yep. So the thing that makes the charges move, all right, the battery moves the charge. And here's the thing that the battery does not do. The battery does not make the charge. The charge is already in the wires. All the battery does is push the charges that are already there. So when we attach the battery to this continuous conducting path, all we're doing is we're making those charges which are already in the wire, we're making them move because now they have some energy and that energy is provided by the battery. So the battery moves the charge because it provides energy. And that, I think, is a pretty good place to stop. So I'm going to go ahead and stop recording.